Regions of revolution are a common topic in calculus classes, and it might be a little bit mysterious why they're part of a calculus class, but actually, when you think about it, they show up all over the place, and part of that is because they can be manufactured very easily and very accurately. This machine here is a metal cutting lathe, and its job is to cut volumes of revolution out of various materials such as metal or wood or plastic. Lathes are perhaps one of humanity's earliest precision machine tools. They've actually been found in ancient Egypt, and most people around the world have had some kind of lathe that they've used to make various kinds of objects. And so this particular lathe is a metal cutting lathe, although it can certainly cut wood and plastic. And I use it mostly for making clocks and parts of clocks. So for instance, here is a part of a clock. This is the anchor escapement portion, and it sits on a little axle or an arbor. And you can see that the ends of this have these shaped tips, these shaped pivots. And those shaped pivots are volumes of revolution, and I cut them using this lathe. But they show up in other places too. So here's another clock part where there's a small hole through a cylinder. But they also show up in machines. So for instance, a steam engine piston. So this has got a cylinder, and it has a piston that fits inside very precisely. And finally, they show up in hand tools too in many other places. So for instance, here's the handle for a wood plane that I cut out of a piece of wood, again using this lathe. Now this lathe can cut very small things as well, things that I would need a microscope to show you. I've cut very small screws with it and small other parts for watches. And so it can cut big and small things. Now, just a word of caution before we proceed. Although a lathe is a very useful and powerful tool, it actually can be quite dangerous. You need to be trained in order to use a lathe. I was trained in college as part of my engineering training how to use a lathe safely. If you don't set it up properly, it can injure or kill you in a blink of an eye. It's a very powerful tool. But with that aside, let's start to see how this machine works. So what it does is it has a headstock that rotates. So I have it set up to rotate at a very slow speed, so you can see it. And so this headstock is rotating around, and this is a piece of aluminum that I can cut. Now, what do I use to cut? Well, I have this particular cutting tool set up here, so it has a sharp edge on it, and that sharp edge fits inside this carriage, and the carriage can be moved in two dimensions. So it can be moved laterally or axially, parallel to the axis of revolution, and it can also be moved radially in and out. You can see that it's taking a lot of twisting to move it in and out. That gives me a lot of precision. When this lathe was new, its accuracy was probably about 1/1000th of an inch. That's a pretty small amount, and that's what the gradations on this lathe are, is in thousandths of an inch. With some tricks and a little bit of trigonometry, you can easily get this to cut to an accuracy of about 1/10,000th of an inch. Now this lathe was made in 1944, and it's been used for a long time by many people previous to me. So some of the gears and screws are worn out. So when I'm reading out the gradations on this particular machine, I'll get maybe 5/1000ths of an inch. But again, if I play some tricks, use a little trigonometry, I can get down to a 1/10,000th of an inch of an accuracy pretty easily. So with that, essentially the idea is you spin up the lathe, get it spinning, and then move the cutting tool in order to cut and carve out your part however you want it. Now, the purpose of this video is to show you how to find volumes of these regions of revolution. And there's essentially two ways to do this. There's a way that's called cutting by washers and cutting by shells. The washers method is simulated on the lathe by cutting perpendicular to the axis of revolution. So here the cutting tool is moving from left to right, cutting into the piece of
aluminum. Until finally it cuts through. On the other hand, the shells method, the tool is moving from front to back, bottom to top in this particular video, moving towards the headstock of the lathe, cutting out a thin shell off the outer surface of the rod. Let's find the volume of this cone by the washers method, slicing it perpendicular to its axis of symmetry. If we do that, each washer will actually be the shape of a disc, like this, and we'll sweep from bottom to top. So here's one of the washers, and another washer might be this one here, and another one might be this one here, etc. This one here, etc. We'll sweep through all of those washers. Okay, so let's use the washers to find the volume of a cone that has a base radius 3 and height radius 7. So in order to do that, it's important to actually draw a picture. So it has a base radius 3 and height 7. So the cone in cross-section looks a bit like this, although we really don't need this bottom line. Each of our washers will be a little slice like this. Let's label our axes as X and Y. We need an equation of this top line here. This is a line, so we need an equation of a line that goes through these 2 points. I guess it is a y equals format's probably the easiest. Y equals 3. That's the y-intercept. The slope is negative, and for 7 units of x, it goes down 3 units. So something like this ought to do the job. And you can quickly check that if I put in x equals 7, I get y equals 0. So that's this line. Now this line actually describes the radius of the washer. And the thickness of the washer is delta x, the thickness being from here to here, delta x. Now, of course, when we start integrating, it will become dx. Okay? Now, what's the area of the washer? Well, the area of the washer should be dx times pi, whatever the radius is, squared. And we're going to integrate this from x equals 0 to x equals 7. That will give us the volume. So the volume of the cone is the integral from 0 to 7, and that's x equals 0 to 7, of pi, radius of the washer, squared. Okay, this presents no particular problem to evaluate, and so we can just go ahead and do that. And at this point, it's just some basic integrating polynomials. And I'll leave the rest of the algebra to you. So that's the volume by washers. Now let's find the volume of this cone, instead using the shells method. So instead of the shells, instead of the washers where we cut perpendicular to the axis, with the shells, we cut parallel to the axis, and we'll get hollow cylinders instead. So they'll look a bit like this. So here's a hollow cylinder, and as we slice along, the next one will be something a little bit like this. It'll be a little bit wider out, and so on. So we'll sweep out the shells. So let's find the volume now by shells. The information that we had for washers is already useful. In particular, the radius of the cone as a function of x is still useful information. So let's just copy that information. But now, instead of dx, we need dy. That's going to be the thickness of our shell. So the thickness of our shell is going to be this direction, and it will be dy. So it is convenient to rewrite this as x in terms of y rather than y in terms of x. Easily done, just a little bit of algebra. Okay, and so what is this x is now telling me the height of the shell. This is this is the radius of the shell. No, this is the height of the shell. And what's the radius? The radius of the shell is y. So what's the volume of a cylindrical shell? Well, it's essentially the circumference of the circle times dy times the height. So 2 pi times the radius times the height times the thickness, dy. Okay? So putting these together, the volume of the cone is integral, now in y, and of course this is not too hard. This is just an integral of a polynomial. So I'll leave you to do that. Now here's a bit more difficult of an example. Finding the volume of this sphere that has a hole drilled through it. This is a sphere of radius 3 with a radius 1 hole drilled through. Again, we could use the shells or the washers. So here's what shells would look like. So here's a particular shell. You can see a cylindrical portion with a hole drilled through it, and we'd sweep them from the inside to the outside. But as it turns out, this is a bit difficult to do correctly and involves a lot of algebra. So instead, I think it's much easier in this particular problem to use washers. And now the washers very much look like an actual washer. It's a disc with a hole in it. And as we slide our washer along, we'll get washers of different sizes, although you'll notice the center hole stays about the same. Actually, it stays exactly the same. So to find the volume of this radius 3 sphere with a radius 1 hole drilled through its center, we're going to use washers. And even though we've seen a nice 3D plot of what this looks like, it's really best to draw it by hand. That way you can mark it up. So let's do that. So here's our radius 3 sphere in cross section. It's a circle. We only need half of the circle, of course. Here's the drilling, radius 1 drilling. The washers are really just going to be this region right here. This is dx is the thickness. It has an inner and an outer radius. The inner radius is 1 all the time, because this is a drilled hole with radius 1. The outer radius, well, comes from the equation of a semicircle. And it's radius 3, so that presents no particular problems. So the volume of a typical washer well, it's pi times dx times the radius squared, right? Well, don't forget the inner drilling. It's the outer radius squared minus the inner radius squared. And you can see why I chose washers rather than shells, because I've got a square root that's going to just get squared. Okay, now the only remaining difficulty here is the fact that we need to know the starting and end x values in order to write out our integral for the volume. We need these points, the x coordinates of these points. Well, after a little bit of thought, you can probably see that there's a right triangle here. It's a right triangle that's got a hypotenuse 3 and a height of 1 that sort of fits inside that drilling. So all we need is the length of this leg. That's square root of 3 squared minus 1 squared by the Pythagorean identity, Pythagorean theorem. So that's square root of 8, or 2 square root of 2. Putting all the pieces together, what we find then is the volume of the region that's the integral from minus 2 square root 2 to 2 square root 2 in x pi 8 minus x squared dx. Now that's not a particularly difficult integral, so I'll leave that to you, but that's the volume of this region.